Welcome back to our fall school second session, with the opening it's the third session already. It's a hard talk before lunch, but I think you will enjoy it. There's one question already starting. The slides are not available now, but we will create a YouTube list with all the talks from the fall school as every year. So if you're interested in the talks from the last years, go to the Ease Learning Hub and you get all the infos on all the talks since 2018. So this is possible, and as soon as Giulio will send us the slides, we will publish them on the page. Okay, so Michael, thank you.
Yeah, thank you.
Now it's you.
Okay. Cool. Yeah, we just had the pleasure of listening to Giulio's great talk, right? And I think, in particular, you as a doctoral student, you can take a lot away from these talks, right? And I think one of the messages you should have gotten is that actually building these systems is a research quest, right? It's probably one of the kind of boldest science questions that there is to solve, to understand how can intelligent systems intelligently act in the physical, but also in the social world to achieve their goals and avoid damaging things, right? I think the other message you should have gotten, right? So, because it's a quest, right? So actually a whole research community is working at different ends and having different perspectives, right? And they are all bringing things to the table, kind of insights that we have to build on, right? So, and Giulio was emphasizing all the things that that neuroscience is bringing to the table and the insights that we can basically take from their field and put it into cognitive robots, right? He also emphasized the thing that if we really want to be successful, it's about the interplay of science and engineering, right? So he said kind of neuroscience and kind of technical implementation, but I think it's more kind of science and engineering in a more general case, because so that's the reason why our collaborative research center is actually called Everyday Activity, Science and Engineering, right? And that bringing these two together is actually something that can create big things. And the reason why that is the case is if you're looking at the science, neuroscience, right? So neuroscience tries to understand kind of the most successful apparatus in that we know in the known universe that can actually intelligently act in the world, right? So we also know it's not only the most powerful entity, but it's also the most complex one, right? So it's kind of hugely complex, and we have no clue whatsoever how it's actually kind of working, right? So engineering, on the other side, right, brings something different to the table, right? So because engineering is a synthetic science, we can actually take partial understanding of the scientific part and try to build models of that, right? And in particular, generative models. So if we have hypotheses of how certain things might work in the brain and how it's actually generating successful actions, So we can take these ideas and try to build kind of computer models out of that, right? And if we are building computer models out of that, we can take these computer models, kind of throw them at the kind of problem domains we are interested on and see whether they work, right? So there seems to be a huge synergy between engineering and science that we can build on, right? And that we should build on. And I think Giulio has also emphasized on what it is, these kind of artificial things we should look at and build, right? And he said it's cognitive architectures, right? So the hypothesis is if we are looking at intelligent cognitive agency, right? So that it's kind of an orchestration, kind of a very complex play between many different components, between many different computation processes that work on kind of very different representations. And we don't know what the representations are, we don't know what the cognitive processes are, but if we have some hypotheses about them, we can actually make experiments, right? So we can build computer systems that take these hypotheses, implement them, and see would that actually explain intelligent agency or some aspects of it. And this is, I think, how we have to make progress, right? And yeah, so I'm taking kind of a bit a complementary view to Giulio's one. So I want to basically look more at from the perspective of engineers and how we actually make guesses about some representations that underlie intelligent agencies, some of the processes, and again, Giulio has kind of pointed at one of probably the most successful or kind of the most essential cognitive capability, namely prospection, right? Imagining the future and kind of the actions we want to do, even if we create new actions that we have never seen before, right? So that's kind of the motor towards kind of intelligent systems. And it's also like Giulio said, it's that process that is actually producing intelligence, and it's not kind of a fixed structure, right? And okay, so let's kind of start. I kind of repeat what I said in the introduction, right? So the fundamental computational problem that we want to understand is we are giving some underdetermined task requests, something like set the table, clean up, bring me something to drink, and whatever that intelligent system is, in particular for manipulation tasks, it has to generate a body motion that achieves the desired effects and avoids unwanted ones, right? And if you are listening to also neuroscience scientists like David Walbert, right? He says, so the reason that we have a brain is actually that we have bodies that we can move, and the only reason to have brains is kind of controlling the motions with which we can change the world around us, right? Okay. So if we are looking at contextualized, as kind of intelligence agency as computation problem, right? So we are interested in, we are having certain objects, certain tasks, environments, context, and we are interested in the behavior that the robot should actually generate in order to perform the particular task with the particular object in the particular environment, given the context that it's in, right? And we can imagine that this is actually a function, right? So like DeepMind puts it in the robotic transformers, right? So we are just, we take it as a huge function, and we collect lots of examples in all parts of the function. And we want to interpolate essentially between the examples we have seen. And you see that we are making kind of fast progress on that, right? So this mechanism works, as we have already heard, in particular for habitual behavior, for kind of parts of actions where you have many, many different examples, the things you do daily in your chores, and you don't think about it, right? So they just go there and you do the right thing, even without actually consciously thinking about it. And I think that part of intelligence, we are really making kind of progress. So when you look at our research, right? So we are interested in kind of robots that can accomplish everyday activities, and we take kind of the daily work of a robot, and the daily work of a robot, we say, well, there are 3 meals in a day. It's kind of breakfast, lunch, dinner. The robot has to set the table, clean the table. We can actually push the complexity by including meal preparation tasks. We can add kind of other cleaning tasks. And we can look at that, what happens if we want a robot to do that kind of over a lifetime of a robot, right? So that's kind of the game that nature plays. So let me show kind of, Gayan is explaining the system. So.
Hi, my name is Gaia, and I'm a PhD student at the Institute for AI at the University of Bremen. In this video, the PR2 is performing the household marathon demo of the EASE project. The idea of the demo is that the robot executes different variations of mobile pick and place, whereby it needs to act completely autonomously with the minimal amount of human interference. The first task is to set a table for cereal breakfast for 1 person. This involves 5 objects: a bowl, a spoon, a cup, some milk, and a box of cereal, which have to be brought to the dining table. Afterwards, the table has to be cleaned up, so the washable objects are placed into the dishwasher, the cereal box is placed back into its storage location, and the milk box is thrown away into the trash, as it's assumed to be empty then. The perception system that we use is called RoboSherlock. It employs an ensemble of experts approach based on the principle of unstructured information management. Importantly, it works in assumption-free scenes, which means, for example, that we don't expect a supporting plane to exist for each object. This is required, for example, for the objects in the dishwasher or in the door of the fridge. The motion control framework that we use is called GISCARD. It does whole body control. For the PR2, this means that we control the arms, the torso, the base, and the head simultaneously. It uses a constraint and optimization-based approach with which we can define multiple goals at the same time. For example, grasp the object while looking at your hand, staying away from the joint limits, and avoiding collisions with the environment. The plan executive that we use is called CRAM. It uses the reactive planning approach, such that the plans concurrently perform the motions and monitor their execution. Simply put, this means that if a failure happens, such as an object slips from the gripper, the robot reacts immediately. The sequence of actions and the failure handling strategies are engineered according to a general model of mobile pick and place, and the parameters of actions are inferred at runtime by querying the knowledge base. There are a lot of challenges that need to be solved in order to master these mobile pick and place actions. First, the robot needs to have an enormous amount of knowledge about its environment, the task, its own capabilities, the user preferences, the physics of the world, and common sense rules. Second, the robot needs to be able to execute its actions in a wide range of variations. For table setting, this means that it should be able to get any object from any location in the environment and place it at any other plausible location. The robot also has to deal with the non-determinism and the partial observability of the world, which simply put means that acting in the real world very often leads to failures, and the robot needs to be able to recover from them. And it needs to keep its beliefs about the world in a consistent state, as close to the state of the real world as possible. Finally, in order to reach human-level skill and mastery, the robot needs to be able to improve its performance over time based on collected experience. For more information, please follow the links in the description below.
Okay, I think that's kind of a pretty impressive subspace of everyday activity, right? That the robot is actually handling quite competently, and it's dealing with kind of all the variations and does the right things in the right moments. And it only got kind of that very kind of underdetermined task request in the beginning, right? So it's kind of on the way where we would actually like our intelligent systems to go, right? And the kind of thing we want to do now is the question, can we actually build a computational model that is strong enough to explain how that robot is actually generating kind of intelligent actions in this kind of range of different contexts and with this skill capability, right? And so as engineers, right, so we want to take that as an experiment, right? So we want to write a control program and see, does it work? And do we have a computation model that is actually built on very few concepts that are very powerful, and the interplay of these very few concepts actually explains how that competent behavior can arise. So in our model, so we are basically taking that as our conceptual framework, right? So we say we are interested in that mapping from underdetermined manipulation task requests to specific body motions. And we make certain assumptions, right? So we make assumptions that if we are looking at that computation model, that the kind of the system has to have some generalized action plans. So something like we are able to write for a task like pick and place for all objects in all contexts in the table setting scenario, one plan, and that plan is sufficient to generate the motion behavior that we have seen, right? And we also make the assumption that kind of this generalized action plan, it says something like, go to a place where you believe the object to be, which kind of at the semantic level, we can kind of complement that with a motion plan. So where we only talk about the parts of the robot body, about the different joints it has, and how to move them. And we can also write a plan for that. And if we take those two plans, so kind of there is a gap, kind of mapping from there to there, and we propose to close that gap by equipping the robot with generalized knowledge about the world, about everything, and the robot should use, when it's executing its plan, that knowledge to contextualize the vague instructions for the specific settings that it has in order to kind of compute a specific motion plan that actually works, right? And yeah, so why do we want kind of a generalized motion plan in our system, right? So I guess the people in deep learning say we don't need that, we just learn and the motions are encoded in our network, right? But we are computer scientists, right? So, I mean, when I was at the university where I did my PhD, kind of the professor in the very first kind of lesson, introduction for computer science, he said kind of one of the big things that you have to understand when you are a computer scientist is that a computer program is not kind of, or not only a specifications of the computations that have to be done, but it's also a means of communication, right? The computer program tells you what you as a programmer think about how you want to solve the problem, and tries to kind of get that idea into syntax, and kind of if that syntax is actually matching the problem and representing it explicitly, and then you have won, right? And the reason kind of why you want to have that is that the problems that you as computer scientists have to solve in the future in your professional life, they are complex problems, right? And the kind of the problems change, and you have to adapt kind of your computer programs to doing that. So you want to do that as kind of, you want to support that as much as possible, right? And we all have learned in our first lessons in computer science, the way we support that is by using data abstractions, by using procedural abstractions, and composing those things together until we have a program that mirrors the way we want the problem to be solved, right? So that's kind of a very, very strong idea. So we have kind of, so then the question is, if we are looking at the pick and place tasks, so what is the structure of the pick and place tasks, right? So can we actually find a structure that kind of fit all fetch and place tasks? And this is kind of what is essentially in a nutshell in the system. It says, if you want to fetch any object and place it at any destination, right? So the robot has to position itself at a place where it can see and reach the object, right? And when it can see and reach it, it can actually kind of fetch the object. So we are hand waving about how the object is actually taken and fetched. And so if we are basically kind of sketching the plan in this way, we put a lot of burden on the cognitive system that is executing that, because it has to make all the right decisions when it's interpreting that kind of plan, right? So if we are going that, if we are doing so much hand waving in implementing our plans, we have to kind of give the robot kind of the system the means for filling the gaps, right? And this is by equipping the robot with knowledge, and in particular generalized knowledge chunks. So you want to say something like, cups used for table setting have to be clean and unused. Cups in cupboards are clean. Cups have to be grasped from the outside. And the power of these things is that they are general, right? So they are universally quantified, and they apply even to objects you don't know that they exist, right? So if you kind of find later a new cup, right? So that kind of knowledge applies automatically to that. So that's kind of a story for intelligent robots to actually deal with the open world, right? And the reason that it can deal with the open world is that it creates for itself a model of how the world works, and in particular it creates a model of how the world works that helps it to act kind of successfully in the world, right? So that's kind of the essence of intelligent agency. But kind of one of the things is kind of the knowledge that are facts, right? But there are other kinds of knowledge. So something like you should parameterize your motions to avoid unwanted side effects. So this is kind of a very, very powerful chunk of knowledge, and we have talked about that kind of knowledge previously, right? So this kind of knowledge requires you to look ahead of time, to actually predict the consequences of action, to decide whether you want them, and if you don't want them, you cannot do the action, right, in that way. So it's actually that the knowledge chunks are not only facts in a logical language, but they can be realization of very powerful kind of cognitive processes, right? And you can say things like spilling is an unwanted side effect of pouring. So there are also other kind of pieces of knowledge which are extremely powerful, kind of if you include them, right? So if you think about, you kind of want to take your fetch and place task, and you want your robot to play Go, right? So then you want to have a generalized piece of knowledge, the next best move in a Go piece, in a Go game, right? And if you want to have something like that, right, so you can have a knowledge chunk which just calls AlphaGo and says, give me kind of the best next move, and you're executing it, right? So kind of the lesson is, if we are thinking about generalized knowledge, right? So one thing is the chunk of knowledge that is there. The other kind of piece of the story is, what do we have to do in order to get that respective piece? And the implementation of a chunk of knowledge can be extremely complicated. It can be any of these powerful cognitive processes that Giulio has talked about. But because we are now putting them as generalized knowledge pieces, we can actually compose them. So we can put them together as we need, and we can instantiate them for the specific context that we are looking to. So that's kind of an extremely powerful idea. So what about the motion plan? So again, looking at what robotics transformers are doing, right? So robotics transformers kind of are predicting how the robot gripper is moving in the image that they are seeing once you have a kind of the task you are given and the image you are seeing, right? So, but that kind of system is lacking essential components of what it is to move intelligently in the field, right? So if you want to move kind of a robot arm, you want to kind of move the robot arm so that it avoids collisions, right? So that it moves optimally that it actually creates motions and particular forces that achieve the desired effects, right? So kind of system that only learns from example doesn't have these concepts, right? And that makes these systems weaker. So Simon and Malte is actually looking into kind of how to do that and how to write actually motion plans that fit in that framework and kind of can create the right motions, right? So we are using, again, we take inspiration from cognitive psychology of action that tell us how kind of fetch and place tasks are structured into motion phases, reach, lift, find spot, that they have a goal state that want to reach. And we refine that because kind of this is done from neuroscientists, right? So that they look at people performing the actions, but they are not creating the actions, right? So they can hand wave a bit. If we want to build a system that is actually creating the motions, we have to go at a greater detail and go all the way down, right? So yeah, so you want to have a motion control framework that you can talk intelligently about it, right? So if you see in a video a person pouring something from a bottle into a bowl, right? So the thing that you want to extract about the motion is that the person keeps the bottle upright, right? So that it's, if it's a pot, that it grasps it with two hands, that it holds the pot horizontal, that and you do that because you want to avoid spilling. Then you take the pot by the handles, and these are the essential components of motions, right? And you want your control system to actually take these essential components of motions and ensure that they are enforced, right? And you want to do that because you know if you're watching a video and you execute it, you have to execute it on different objects with different purposes, and everything is different. You have a different motion, a different body, and these things have to carry over, right? Again, to represent these motions explicitly as a model is giving that reflects the structure of the motions. It's what puts you in a position to win big time, right? And yeah, and so you kind of want to kind of get things more acting in with a dynamic world and. Yeah. Okay, so we have that. So contextualization. So this is essentially the essential inference step that in our kind of model happens, right? And so whenever the plan interpreter is doing something, it gets an action description like this one, right? Perform an action of the type fetch and place with an object that is of type cup, and the destination is the kitchen table. So we have seen these generalized plans, right? So when we get essentially such action description, we select a generalized plan that we can use in order to execute it. And then we take kind of the action description and extend it with all the parameters of the motion plan that corresponds to that action plan, right? And we instantiate the attributes that are specified in the task request. So we kind of substitute the expression an object type cup for the general object, right? And if we are doing that, so the whole control system can work by repeatedly kind of asking the body motion query, right? So we know what the variables are in the motion plan. We know what it is that we know about the action at this moment. And the question is, how should we set all the attributes of the motion to make the action successful, right? Kind of the good thing is, it's kind of one question that the system kind of has to answer. Kind of the bad thing about this is that the machinery that actually is needed in order to answer the question is very heavy, right? Because it kind of has to build in prospection, it has to build in experience-based learning, things have to be brought together. We want to kind of execute optimization-based and constraint-based motion planning. And the question is, if we are throwing all these machinery together, how do we actually get the consistent refinement? And that's kind of what the cognitive architecture has to do for you. So this is our cognitive architecture that implements that idea that I've just talked about. So you see the components that I've talked about, the generalized action plan, the motion plan, the plan executive that is executing the system is creating always the body motion query, the knowledge representation and reasoning system with the generalized knowledge is answering it, giving it back, and we have our motion execution system and a very competent perception system that assists in doing that. So that's kind of what it is. So in the remainder, I want to talk a little bit about the knowledge representation and reasoning that goes on in such a system in order to make that competently. So, and we, again, so we are repeating, right? So the essential thing that is in such a system is the representation of the model of the intended action, right? So that's kind of the fundamental thing we want to have kind of as a basic representation in our robot control system, right? And it kind of that model should be strong enough to actually be derived from underdetermined action descriptions, be detailed enough to execute them as motions. It should be kind of executable in an inner world model. So the idea is that the robot has a game engine in its head, and whenever it's intending an action, it actually uses its game engine to make predictions about that action model. And the whole thing then should be machine understandable, right? Because the robot has to do the open question answering task when it's executing the action. And that's kind of what we are aiming for. So the cool thing about our current state and why this time is so exciting is that we have the computation tools to make substantial advances on these representations now, right? And kind of the big computation tools, it's the same as in deep neural networks where we suddenly have kind of very big networks, kind of immense amount of data, immense amount of computational power you learn. The same happens for actually modeling the intended actions, right? And the reason is we have these game engines, right? So the game engines, they are able to actually represent that room here with everybody in here, a model of everybody. It's kind of, it can be updated real time if you kind of use the NVIDIA machinery, right? So you have a scene graph. A scene graph is a data structure. So if in your robot you take that scene graph, you kind of maintain it over time. You have a data structure where kind of you have all the information you can possibly get about producing the right actions, right? And that's kind of a very big thing that we are now able to do that we have not been able doing at all. The other thing is, because it's a data structure, it's an implementation, right? So, and we can basically turn that data structure in knowledge, in abstract semantic knowledge, right? So we can have something like a predicate, object A is on object B. But we are not kind of storing that explicitly as a symbolic fact, but we say, oh, if the query on AB comes, I take A, look at what it is in my scene graph, and I look what B is, then I look up kind of whether A and B are in contact, and kind of maybe whether A is above B, but whether that contact is actually canceling out gravity force, right? And it doesn't move despite kind of being somewhere, right? And that's kind of a perfect implementation of being on, right? And you can imagine that your knowledge that you need in order to act intelligently in the world, it's just a virtual kind of knowledge base where you have predicates, they look like facts in a symbolic knowledge base, but they actually compute that truth value on demand out of the scene graph, right? So that's kind of extremely powerful, right? Because then you're looking at your scene graph of that of our room here, and you know that everything is depicted in that kind of photorealistic image is also available as a symbolic fact, right? I can ask about it and the system can answer it. I can ask the question, give me the kind of the handle of all electrical devices that are used for storing food, right? And kind of in the scene graph, we could highlight the handle of the fridge, right? And this would be the handle that the robot has to open in order to get the cold milk out, right? And that's kind of the game that we are playing. So yeah, so that's kind of that. So we have a scene graph, we have a symbolic question, and those predicates are actually dynamically computed out of the scene graph. So we build a language, right? So we have predicates like holes, and that can be kind of all the relations like on, like inside, closed, and whatever. We have predicate occurs, so we are in a first-order time interval logic, so that an event occurs over some time interval. And we have entity descriptions, which is just syntactic sugar we put onto the logic language. And then we can ask queries like, give me an action of the type grasping, where the object being grasped is an object of time spoon, and where the kind of action occurs over a certain time interval, and the spoon is on the table, and kind of here we only have a name, but here we request that it's really off the category table and show the table, right? So what's happening is that at any time, the robot control system executing the action description can ask these kinds of questions, right? The system is computing the answers out of the scene graph, and the answers are kind of in a way that we can directly derive the kind of the motion specification that the robot has to do in order to do that action. Okay, so here we have an example. Yeah, kind of asking for the trajectory with which you can put down a cup on a table, and you get that, right? So, as I said, so the power comes from that there are two very distinct representations. You have kind of a simulation environment where you can hook up the perception and action of your robot, and you can mentally simulate your actions using the simulator of the world. Right? We have a logic knowledge base which makes everything machine understandable, right? It kind of translates everything that we have here into a symbolic structure that computer systems can automatically understand and interpret. So the cool thing is, so this can be done by a single data structure, and this data structure is the scene graph data structure of virtual reality engine, where Jensen Huang is actually driving like crazy to make that as powerful as possible, right? Yeah, and kind of, so you're getting that. Yeah, so just give me kind of final example of how powerful that is if we are actually linking the machinery to the perception system. So if we are using the scene graph representation, right, so we can actually define logical predicates like the expected image. We have Julio has made the case, how important is it that perception is not looking what's outside, but is expecting kind of what it sees. So we can have a predicate expected image, right? So we are taking the pose of the camera in the virtual reality scene graph. We take the scene, we render the scene with the parameters of the camera, and that's the image that the robot is expected to see. So we have another, so we want to see, we kind of want to infer how the milk box in the fridge will look. We can do that with the machinery because we can define a predicate image segment, right? And so what we are doing is we are taking the scene graph. We are asserting that every object besides the milk box is invisible. And we are rendering then the image, and we get back kind of the what we expect, the milk box, a particular entity that we see in a scene, right? And third kind of predicate that I want to talk about is depicted object, right? So the one is you're looking at an image, you kind of want to see, you see kind of a particular pixel, what is the object, right? So that's kind of the basic inference. So yet again, taking your scene graph, you assert that every kind of entity in the scene graph has a different color, and you're rendering, right? So now you can ground your symbolic representation in your image, right? Because the pixel color exactly tells you kind of what the object is. So if kind of the image matches that you create in your inner world, matches the image that the robot sees, it can get these inferences for free, right? Okay, so then I guess I have to stop here. As I said, so the kind of thing I wanted to look at is to see whether we can actually take some activity which is fairly general, which requires a lot of competence on the side of the robot, and whether we can actually build a computational model that is strong enough for actually solving that problem in kind of that we wanted to solve, right? And we essentially have proven that if we kind of design the programs the way we are proposing, we can at least do that, right? And I think that's kind of an example how science and engineering should work together in order to solve the big problems, right? Because if you think about what we have included in the conceptual framework, it's kind of a lot of the ideas that have been developed in neuroscience, right? But if you think about how we did that and how we got an operational framework, we used the ideas of computer science, of making models, of representing models explicitly, and the combination of both actually shows promise that we can make significant progress on the essential problems. Right? Okay, thanks a lot.